Modelling influenza epidemic using SRI model is a topic we're going to be talking about today. My name is Chelsea Stevenson, and the other team members that you will hear from in this video are Olivia Sina and Gabriella Oliver. According to the Queensland Government, influenza is a highly contagious acute viral infection that spreads easily from person to person. Influenza is most often caused by type A or type B influenza viruses that infect the upper airways and into the lungs. This disease spreads rapidly through the human population in brief bursts called epidemics. In 1918, over the course of about a year, up to 1 in 3 people in the world had been infected by influenza, and 5% of the global population were killed. This real-world problem has significant repercussions to the population around the world. Mathematical models that are used to track the spread of the virus predict the time course and assess the likely impact of the large-scale vaccination. The mathematical model, which could be applied to the influenza epidemic, was developed in the early 20th century by W.O. Kermack and A.G. McKendrick. This model is known as the Susceptible, Infectious, Recovered model, or the SRI for short. Susceptible are the ones who can catch the disease, infectious are those who have the disease, and recovered are those who have had the disease but are now immune to it or isolated from the population. There are only 2 ways out of the disease, and that is either through the recovered stage or, unfortunately, through death. I'll now pass on to Olivia.
To understand the SIR model, you need to understand 2 different rates. The first rate is the rate at which the susceptible get infected, and the other rate is the rate at which the infected move into the recovered phase of the model. For the purpose of this model, the susceptible will be known as S to the T, the infected will be known as I to the T, and the recovered will be known as R to the T. The T represents the time period at which the data is collected. This means that we have to multiply by the number of susceptibles, or S to the T. Since we multiply by S to the T to get the rate of S to I, the infection rate is proportional to both S to the T and I to the T. If we let B be the constant proportionality, we can then write the infection as B times S to the T times I to the T. B is a single number that combines 2 effects: the likelihood that the susceptible and an infected individual will react with each other, and that such an interaction will lead to infection. If B is equal to a large number, it means that the population have a lot of social interaction and that the disease is highly contagious. This combination will maximise our infection rate. On the other hand, if the B value is low, it would mean that the population doesn't interact with each other as much and that the disease is harder to contract. This combination would minimise infection rate. The next phase is when the infected move on to the recovered stage. Unlike the first stage, this stage only depends on the number of infected individuals. If each infected individual recovers at the same rate, then the rate of recovery should be proportional to I to the T. If we let A be the constant of proportionality rate, then we can write it as A times I to the T. Therefore, A represents how quickly an individual recovers from the disease. If A is small, then the infected person stays infected for a longer period of time. Therefore, they are more likely to infect others. But if the A value is larger, it means that the illness is brief. Whew. To sum it all up, the susceptibles become infected at the rate B times S to the T times I to the T, and the infected recover at the rate A times I to the T. The infection rate is represented by B, and the recovery rate is represented by A. I will now pass along to Gabriel to explain how the solution to this problem helps in real-world situations.